This is a video demonstration of exploit development coursework 1. So we had a zip file out of which we extracted some of the files. So we extracted coursework 1 and a Docker file. The Docker file instructed us how to uh, use it for fetching the dynamic dependencies, which are custom dependencies. So we will be running the Docker first. So I have named it as Coursework 1. Now it's running. First, we will be accessing the Docker shell. So we are into the Docker shell. After that, we will see the file type of Coursework 1. It is elf file, which is built in some libs 64 something LD file, which is not stripped, which let us to see the code of the file and analyze the functions. The functions are printed as it is. They are not named differently. So here we can see LDT C1 C11. So to see the dependencies which it's run on, we have entered this command, and we can see here it have these two files. So I will be copying this file. So we have successfully copied this file. Similarly, we have to copy the file of the LD dependencies too. So I have already copied the file, and these are these files are dynamically linked, so they are broken right now. They are broken, so we have to link it with other file. The LD file should be linked with this file, and this file should be linked with this file. uh, for now I have already linked the file, and I have the running files here. Here are the running files which we are required to use. So I will furthermore first check the file. We can see here railroad is here, stack canary is found, annex is found, pi is executed enabled, stk is enabled, and ibt is enabled. However, strip is not there, so the file is not stripped, which means the function are named as it is. They are not modified. So for patching the file, we will use poninit command, where binary file is coursework1 file, and libc version is libc.so.6, and ld version is this. So we have got here patch file. Uh, okay, this is also a not stripped file. So here we have run path as b and stripped not. So we can see the security of this file. After patching the file, we have got solve file to solve.py. So as we can see here, the solve file contains the how to build a connection over the remote address. So it is defining the port, and the local IP. So we will do the reader for coursework 1 file, patch file. Okay, we can see here we have the different type of functions revealed. Okay, this command reveals some all of the functions right here and some of the data. So if we use this command, we can see the load and GNU stack properties and all. So first we will be uncovering some of the vulnerabilities which we have found. We are in this create index file. So it contains some critical vulnerability due to safe access of heap metadata. Well, the program is attempting to read the chunk size metadata directly from offset. So we can see here this part is vulnerable, and this is taking the input from user directly here. Well, this directly reveal this part of the code directly reveals the internal heap information, which can aid attacker to do further exploitation. And the calculation is adjusted for further operation without boundary validation. So next is heap buffer overflow in edit buffer. We will move toward edit buffer here. Okay, it introduce unsafe buffer size. We can see here local string length. So this part of the code is very unsecure. Well, in this local 20, this gives the buffer value times 8. This redirects direct to the memory location without validating redirect direct to the memory location without validating if the local 20 buffer size is right or not. We will move toward the read into buffer function now. So we can see here we have the read into buffer function. The buffer in this part the else condition is vulnerable because the program attempt to determine the size of allocated buffer manually. However, by accessing metadata stored just before the buffer pointer here, but the function is very much vulnerable to unsafe heap metadata access. It calculates the buffer size by reading 8 bytes before the heap pointer. So this may result in incorrect size and heap corruption in the local 50. So here is also a missing input validation. So the computed size is directly used in read. So the read directly takes the computed size here without bound checking, and the heap data leak risk is also there. If user can dump the content to a file, initialized or sensitive data may expose. So this part is vulnerable from this part of the code. So the calculation does not account for scenarios where buffer was not initialized properly. So if the pointer is corrupted or not, it cannot uh, determine that. So heap metadata abuse, we will check for unchecked memory disclosure. So for this, so we will move toward the right from buffer part. So in this part of the code, in this function, this else condition is quite vulnerable. So it is vulnerable for heap metadata abuse for unchecked memory disclosure. So what it does is local variable 30 retrieves heap chunk metadata from offset typically used for storing size, and it align with bitmask. However, uh, it adjusts local 20 which passes to right here. Uh, this check this uncheck can lead to exploit heap with chunk overlap, so or fast bin attack. So we can probably do a fast bin attack here. So furthermore, we will move to another part, delete file index. So in this part, there is a condition, if condition here, if 0xlf local 14, and this condition here. So what this does is the release memory for the it release memory for the specific buffer index and reset to prior 0 here. While this may seem secure, but lack of validation UAF vulnerability, it is very much vulnerable. So this part is vulnerable too. And another part is command injection. So we will go to list files. In this list files, the get character is quite vulnerable part, and this else one s var3 is also a vulnerable, and ARGB is vulnerable, while the EXCV is the main part which takes the command injection flaw. Well, this takes the command which is prone to arbitrary code execution. So we will move toward how we can exploit, or how we can see what's going on. So in this part, we will demonstrate how we have found the heap value and the chunk value. So we will move further with the execution of this file. We have been executed this file, so we will we will create some files in 0 slot with 248 values. So we will continue it for up to slot 10. So we have created a file up to 0 to 10 index. So we will again remove the file from 0 to 6 index. So for removing the file, delete index 0 up to so we have successfully deleted up to 6 index. So we will again create a file in index 1, index 0 with 248 value. We will try to read it. So we have successfully created the file, and we will try to view it. Slot 0. So we have got a leak here. So if we try to create a file with something Jabris value, so it will be giving a create file index error. So here, if I try to create a file in slot here with 248 values and try to read it, So here we can see view 248 values in slot 0. So furthermore, if I want to read the file, I'll enter this one, enter this slot 0. So if I want to enter my file content, I'll use this cyclic 299 value, and this gives with the enter file slot to read into Coursework 1 patch, read into buffer error. So now we will be having a review for the exploit. So here we can see we have the exploit. It is written in the Python. So we can see here we have done the setup for architecture. The Coursework 1 file is loaded here with the binary file attached to it, which is needed for the exploitation. So first we are establishing a connection. It can be a local or remote. This memory allocation is typically used for this part, creating file. Deallocation is typically used for this deleting file, and override is used for read into file. View is used for display file, and modify version is used for editing the file. So furthermore, we will be moving towards the population tcache here, populating tcache. So we can start by establishing a connection to the target and the tcache. To exploit this target, we will be manipulating the tcache in memory cache by using glibc fast allocation. So we have used here allocation here and deallocation here. Deallocating the memory chunks, we will fill the tcache with specific chunks. So furthermore, this leaking heap address, it is actually used for leaking the base address. So we have used display here. We allocate memory chunk here. Allocate is used and perform view. View is done and read the chunk. Display is done. This information is used to read the leaked data from the heap, and crucial because it allows us to calculate the position. See, we have the calculation of position here, this is the value which we extracted from GDB and GitLab before to calculate the position of the memory structure and control this in subsequent manner. And furthermore, null byte injection, we execute a null byte by injecting null byte. We break string. See, here we have overwrite and modify the strings, which disrupt the program interrupt data, and this technique let us to overwrite chunks in way that we prepare to binary for next step exploitation. So there is the leak and libc address here. For this part, at this point we leak the libc address here. See, here is the display display function being used. The address tells us where the system and libc is loaded. It is important for calculating the address of function like malloc and free. So next one is clearing the tcache. In this part, we clear the tcache by freeing some of the allocated memory. Here we can see here deallocation is used. This step ensure that our next operation will allow us to overwrite critical memory locations. Leaking the stack address. So for leaking the stack address, we manipulate the memory to reveal the address. So here we have used display and allocate. The address is crucial for return oriented programming, which is used for control program execution in flow later. So leaking the text segment, it is using the allocate memory display memory part. So what it does is it leaks the address of .text segment containing the executable code. This is this address let us to determine where the program code is located in the memory. This is necessary part for furthermore execution. So override malloc hook. So this part we override the malloc hook. Here we have overwrite function, which is overwriting the file entry point and some values which we have extracted from GDB and Ghidra. So the malloc is the function pointer which used by glibc for memory allocation. By controlling the pointer, we can redirect the execution to cell code. See, here we have the redirection for our cell code or RC or anything. So modify the value one gadget here. We have used here one gadget for the exploitation. So furthermore, triggering the RC, we now trigger the one gadget RC which we use in override malloc. The most crucial part is here. So that's the reason why we are calling this part of the function here. This help us to redirect execution on one gadget RC for arbitrary code execution. So last is gaining the cell. For the cell to be stable, we are using the P interactive. So now we will be doing the pawning the cell. So we have already here Docker running in our background. So we will run this Python script. Here we can see that some of the leaks found in our program are being revealed here. So we have successfully demonstrated the pawning of cell. This is the successful video demonstration of the Coursework 1. Thank you.